All right. Um. Hi guys. It is I again, and today we're back with another stream, and this time we're streaming Virtual Circuit Board, a game that I didn't stream for quite a while, and I recently got back into it, and I was like, all right, let's do something, or anything really, and also, don't mind any background noise. It's raining right now, and I left the window open so that we have some clear air in the room. Either way, let's get started. I'd say. So, this project right here is a 16-bit CPU. So far, I have this done. That in the top left corner. That's just a Russian alphabet I made for whatever reason. I don't remember why I did that. But so we have this like three main clumps of circuit. Now what are these three parts, right? This right here is the VMem interface. So here's what the memory gives out, and I put like my own custom registers around it so that I can write to it as well in a very compact way. And this right here is the program counter. It is a tad bit confusing to look at first, but essentially there's a bunch of modes on it that you can use. So by default it just increments, right? But if I toggle this little latch, so this switch, then instead of adding like just one to it, I can add a custom number to it, which essentially means Jesus Christ, which essentially means that I can not only jump to an absolute label or anything, but I can also jump relatively, which I'm not really sure why I would do that. Not sure why I would do that. Probably I don't know really. I don't know. And then there's the second switch. What the second switch essentially does is that instead of taking the output of the adder into the registers, you take a custom input and put it there. Which essentially means that it's a jump function, okay? And registers are automatically always updated. So that means that in between clock ticks, let me just start the simulation. So in between every clock tick, you have time, to decide like what you want to do. The clock is set to a fairly slow cycle, and it's decent. It's decent for what I need it for. So yeah. Oh dear. My computer is having a meltdown. Don't mind that. It's probably gonna happen every time I run a simulation, because VCB is like really heavy on just one core of the CPU, as far as I know. So anyway, ignore this big circuitry. All you have to know is that there's like this part, which is the program counter part of it, and this part, which is just the input, which is the input-output part of virtual memory. So that is the VMem interface clump. This part is probably gonna connect with that, because this is the call stack. This is just a regular stack module put a bunch of times down with little like controls. All you need to know is that this is essentially what's gonna use these extra buses. Like for example, see this bus here that comes out from the adder that always contains the next address. That it's always the next address that you're gonna be going to. Now the thing is that if you pay close attention, this is actually connected to another part, which is this. meaning during jumping you can't really use this bus. However, you can use the output directly from the adder, which is right here actually, which I might actually just extract, like over here, because then you can just use the direct output of the adder, which is again always the next address, and you can put that into the call address, which is why it's important, is because when you encounter a call instruction, when you return, you want to return to the next instruction under the call, because then you would be, you know, stuck in an infinite loop, calling and returning and calling and returning. But this way, if you take the address one after, then you're gonna be jumping to the instruction after the call. So that is very neat, and that's really nice that I can just take that out of there. And of course there's gonna be an output, which is then gonna be just put into this bus line here, which I don't know why I extended that way. I don't even know where I want to put stuff, really. This is really heavily in work. That's why I decided to stream today, because I just want to, you know, show you guys, like, you know, how I work on these CPUs, especially because some time passed since the last VCB stream, and since then I'd say my skills have gotten better, I guess. Not to glaze myself or anything, but, you know, I'm not as outright terrible at VCB as I used to be. Like, especially when I was streaming, like my first making CPU videos, those are just like a crime scene. I mean, everyone starts somewhere, but, you know, there are limits. So then again, now that I explained what these two are, there's obviously a third clump, which is right over here. That guy is an everything. It's like a little bit of everything. So let's walk through. This is technically supposed to be the ALU, which isn't complete yet. There's some parts I want to add to it. So anyway, let's look at what we have so far. So here, right here, we have a register file. Very easy to recognize. There's a little section up here at the top. This essentially just like helps you decide whether you want to take the output of the ALU or the output of the register, which means that if you want to take the output of the register, you can just technically write back into the register. So yeah, it's like a write loop. So why does this matter, right? It's just moving between registers, and you don't have to use the add instruction or any other ones. So ignoring that, let's go further. So you can see that I've taken a direct output of the last register in this file and put it into like this smaller adder and redirected into the second cable. So let me walk you through. This part is an incrementer. It's designed to be an incrementer, and it is for the stack. So yeah, I know it's a bit confusing, but essentially for that I'm gonna explain this later, because I'm gonna explain the easier ones first, and then I'm gonna explain the stack, because the stack is a bit more complicated and not just the regular one that I used in another 8-bit CPU, which I am going to show you in a second for comparison. So here, this is a 16-bit adder. You can recognize it from the program counter. It's literally the same model, just with, you know, some extra wires around it to turn it into like an adder slash subtractor. There's also some flags that I took out of it, which is the 0 flag and the negative flag, and using those two you can get like all three necessary conditions, which is the greater than, less than, or equal to. Now these three all have positive and negative versions. This means that if it's on, then this is like the case, you know. So for example, if less than is on, then that means that A is less than B. However, if it's negative, then that means that A is greater than or equal to B, which is very nice and very neat. You know, you can use it for quite a few stuff. And there's of course equal and not equal. Those are pretty straightforward. So over here we got a logic unit. This is essentially just AND, OR, XOR, and NOT put into like these rows, so that you can use you know, logical operations, bitwise logical operations on values. But that doesn't matter right now. What does matter, however, is the stack, because you can see first off it's gigantic, and that is not because I'm using registers as part of it, because here comes the explanation. So see, this is a 64 deep stack, so there's 64 slots in it, which I'm gonna need because this is gonna be probably one of my biggest projects yet. And so the reason why we need this, it's a tad bit complicated, but essentially how stack works in real life is that it's not actually what you see. Let me show you. So in my first CPU, it's an 8-bit CPU, you can see that it has these weird models. These are essentially just shift registers with like an extra read attached to them, so you can read any layer. So why this is important is because so it is important because this one you just push, pop, and you can also read any layer. However, in real life you can also see that you can write to any layer of the stack. You can write to any module, and that is because the actual stack isn't just shift registers in real life. It's actually the same memory that you have the registers in. It's the same exact thing, because your computer functions on just one big chunk of memory. So technically this still isn't accurate because I'm using two separate memory modules, three because I also have a call stack. But anyway, the stack is essentially just a gigantic memory, and it has a pointer, which is the stack pointer, which is this last register that I took direct output from. And essentially why you need this is because this pointer is because that tells you relatively where you want to write, where you want to read from. Literally that's it. And so let me explain how this works. So there is this register which has input directly ripped from it and inputted into this incrementer, which then puts it back into this bus, which means that you don't have to actually read out the content of the register to actually give the adder access to it. So why this matters is because then so this puts it on the second bus, and if you remember over here, this takes input from the second bus, and optionally you can allow it so that it lets through that value. And so when you allow this, and then you also allow the incrementer's value to pass through, that means that you actually allow to change the stack pointer. So how incrementing, for example, the stack pointer is going to look like, which is pushing, is that essentially you, how do I say this? Okay, essentially what you do is you write the value, right? You write the value, and then you go ahead, take this, allow incrementing mode. So that means that it's gonna add 1, just that's it. And and if you do that, and that's gonna, holy shit, I'm saying so much gibberish. Essentially, if you input incrementing mode, then it's gonna add 1 to the stack pointer after you wrote the data, which is very simple. You just pulse probably an AND gate, and that's it. So after that, you're gonna allow this as well, meaning that the second bus now contains the new address. Then you also allow this one, meaning that you want the registers like write line to match with the second read line. So what is inputted onto this line right here, which is it's not brought down. Oh wait, it is. No, I'm stupid. I brought it up. No, this one. Yeah. So this one right here. If you allow input from it, then that means that, for example, if the address here was 27, for example, and you increment that, then the second bus will have 28, and then you allow this so that the input bus also has 28 on it, and then finally, ignoring the decoder, you're just gonna go here, hijack the signal, right signal here, which is very easy to do, and pulse it, which is automatically just gonna move that new value onto this register specifically, and then you disable all those controls, and that's it. So decrementing is gonna work the exact same way, except that instead of adding a carry in, you instead take all of these bits. You take you take all of these bits right here and set them all to 1, which essentially means that you're adding -1 to it. 2's complement, if you're curious, you can search 2's complement, which is a way of representing negative numbers in binary. But either way, it works very well with most adders, I think all adders even. And that essentially adds -1, so then when you pop, you can add -1, and oh, actually, hold on. You add -1. Yeah, I mean, there's multiple ways of doing this. This is the problem. There's multiple ways of doing this, because what actual computers do is that they don't delete the data. They actually just skip over it, like if it didn't exist. And that's probably what I'm actually gonna do somehow. But that means that the write sequence has to be a bit more interesting. Oh no, not actually the writing, hold on, the reading has to be a bit more interesting, because it takes the address you give it and then reads the one that is one less than it. So then that is because, so that means that, for example, if this is where the right pointer is, right on this row, then the read should be reading from this one. So this should be the read one. So essentially what it's gonna do is it's always gonna take what the right one is and subtract 1. And the right one is literally just the output, I think. No, the right one is this. So all I have to do is take this, attach a decrementing device, and then it's gonna hold on, what? Hold on, I'm thinking. So you take that, add the decrementing device on it, and that is gonna show you the read address. Oh, I just realized a funny thing. No, never mind. Oh no, because we're not hijacking the right signal. Okay, we're hijacking like the middle of the actual register, the actual value in it. Okay, forget it. So what we're gonna do is we're gonna add the decrementer to it, and actually, yeah, no, to that, no. Actually, yeah, a decrementer to this, and then another adder module like this. And that is because when you're reading an offset, again, you will need to so when you're reading an offset, you'll also need to, add or subtract depending on the offset. Although it is likely that when reading and writing possibly, this is complicated because when you write to a specific address, if you add, then it's actually gonna write somewhere else in the stack that is gonna overwrite. So what you actually have to do is when you're doing arithmetic with the stack pointer in its own unit, so not with the ALU, but its own unit, then whatever is the input, you invert it, and that's what you give it. So, and that's what we're gonna do probably. So when, for example, here it is. So just to show you, upwards is upwards is where it increments. So going upwards increments, which means that if we add a plus there, then it would normally go up, which then it would later, overwrite, which is not good. So instead, a solution that could be possible is that we could actually invert whatever we get from the input, with say, I don't know, these 6 bits. For example, don't take my word for it, it may be something else. I haven't actually cared so much about software yet. So if we take these 6 bits and use a special unit to take the 2's complement of it, then we can put it into the adder part. So that means that even though in code we're doing arithmetic with a positive number, in reality it's a negative number, so it's actually gonna go downward, and that is what we need, because it just makes it more readable. And so for example, if here's the right pointer and we want to write to this one, then it wouldn't be I don't know, stack pointer -2, it would be stack pointer +2, which sounds much more elegant and much better, I think. And you wouldn't generally use minus, because because if you use a negative number, so like stack pointer -2, then that would be this, right? However, since we're incrementing the pointers upwards, then that means that whenever we write and we step there, we're not gonna check if there's any value, and if there is, then we keep it. We instead just overwrite it, because in real life that's also how stack works. If it has an unallocated point, it's gonna think that, oh, there's no data there, so it's gonna write there, and that's why it's better like this. So yeah, that's a nice idea. Okay, I'm just gonna delete those because it's gonna confuse me later. So now that we're done with brainstorming on how this stack actually works, I explained all 3 of these gigantic clumps. So that means we can get to actually working, and that means first off doing whatever the hell is up with the flags, because when you have flags, you actually want to save them every single compare. So what it's gonna do is that the only instruction that actually updates the flag register, well, flag quote-unquote register, it's not a true register in the actual like register file, it's going to be a separate register. So the only time flags are going to be updated is when the compare instruction happens. So we need a separate register file here. There's a bunch of smaller designs I could use. I'm just gonna be a bit of a simpleton and actually use a less complicated design, because it's gonna make it smaller, even though I don't know what I'm gonna do with this space here. So let's see, what do we want to do? There's a bunch of designs for these registers, by the way, and I keep forgetting them. Okay, you know what? I only remember how to do. Wait, actually, hold on. Let me check on another project. Because in this project, I do have. Oh yeah, perfect. You need this. Save, I guess. There we go. Very nice, except we don't have 4, we have 3, because I don't have overflow anymore, because I realized how genuinely useless it is. And yeah, yippee, I guess. Let's just, oh, it's gonna overlap with the signs. Hold on, let me actually, I'm gonna move it somewhere here. I'm still gonna get the reference, so for my future self. There we go. So you can see that's much more compact. So we can just move a bunch of these bits here, and boom. So that means oh yeah, it has to be updated once at least. So we're gonna attach a pulse to this, and So originally what I did was update the flags every single cycle because there wasn't truly a compare function. You just did it like right after. It's complicated. What I have to do is that I have to pulse it at least once, I think, to set it up. Not really, actually. Hold on, not really. Because the zero flag, we don't care if it's on by default. It's gonna be on by default. Okay, so this is fine for now. You can see that we can just pulse it and it's gonna save. This is very nice. So now that we have that, we can stop caring about flags because technically they're mostly done. And there are some more ALU operations that are missing because I did have some in mind. Especially what I want to have hardware coded is multiplication and shifting. Now technically you don't need shifting if you have multiplication. Oh Jesus Christ, multiplication. But multing is a long operation, and also shift has many varieties. So there's shift left and shift right, of course, we will have those, but we'll also have circular shift left and circular shift right. Now the difference is very obvious. The regular shift, if there is, you know, a bit that's gonna go out of bounds, it doesn't care, it just shifts it out of bounds, so that means it kind of deletes that bit. However, what circular does is instead of shifting it out of bounds, it shifts it around, like if it was, you know, like a circle. Hence the name circular. So both of these are probably very important. So how do we want to do this? I'm wondering how I want to do shifting because there's a bunch of ways to do that too. The most used one is combinational, where essentially you have like multiple layers and each of them shift by a different amount, and depending on which ones you allow, depending on the bits, then I don't know, if you allow 1101, that is 13, then you're gonna shift by 13 to, I don't know, the left. Now these shift units, as far as I know, aren't that hard to make, especially since we have these beautiful things called buses. So I'm just gonna design one module. It's gonna be very simple because what you do is you take, hold on, let me think. So you take a trace, obviously you have to read into the gate, read. This is the shift, if you want to shift, you know, and then we want to write to the next layer. Hold on. You want to write to the next layer, how? Because we don't want overlap, right? We don't want it to overlap. Actually, I can put it probably here. I could get away with that. Because there was a 4x4 module, I remember that. I'm just not sure how it was built. Hold on. Maybe like this. I think I have it. No. Okay, hold on. Excuse me for a moment. So what I'm just gonna do is real quick find that module, because I am pretty sure there was a barrel shift, I think. Hold on. I think this one. Ah, yes. Yeah, this one. So I'm just gonna take this real quick and go back to VCB. So let's delete this. We don't need this. So this is the module. Oh Jesus, why does it use so much traces? Oh no, why does it look like that though? Hold on. How does this work? So if I stack like 4 of, oh, wrong direction. So wait, what? No, this is confusing. Hold on. No. This is probably not what I want. This is definitely what I don't want to use. 8-bit shift circuit. Where is it? No. Let's see. Ooh, what is this? Unidirectional. Where? I love Discord when it comes to jumping to messages. So reliable. Let's see. What is this? Ooh, that's. Oh wait, it's a shift register. No. 3x3 shift register. Okay, I can't seem to find anything. Ooh, what's this? No, that's not. Okay, well, scratch that. I'm gonna make my own. Here we are. So I'm gonna make my own because I don't have the patience to be searching for God knows how long, you know. Okay, how did I do this? Here was the trace. I just noticed an erroring render, like a rendering error. Okay, 2D looks way worse. So if I do this, and then okay, it's gonna look terrible, but it's gonna look like this. And what I'm gonna do is take this module. I can't really oh wait, no, I can stack it closer. Ho ho ho, suck my cock. Okay. Now we can take 16 of these, and that means that we can also shift them up. And we'll need 4 layers in total. And this looks beautiful? Question mark. So, let's see. I'm gonna first do circular shift. So 3 offset, and this is the inputs, right? 1 to 50. Now, if I set it to 1, graciously, and it's gonna calculate like that. And this means that we are shifting to the left. So this is gonna be a circular left shift. So the next one is gonna start from 2, then the next one is gonna start from 4, and then the next one is gonna start from 8. And with this we can do all of the shifts, I think, except shifting for 16, which essentially just discards the entire value. So there is not a lot of reason to include it. Okay, so this should work. I'm just gonna do a quick test here. So I'm just gonna add a bunch of these switches so I can use it here. I'm also gonna add an input layer, which, let me see, 16, this, oh no, right, and a bunch of these. So, you know, just as a test, and I'm just gonna put, I guess, a bunch of retraces because those light up clearly. There we go. So we can test it already. So if I enter 3, oh no. Oh god, I'm stupid, and that's also not good. Wait, what? Hold on. 0 goes there. What? 0 goes there. Oh wait, this is shift right. I'm stupid, but I also screwed up. Wait, what? But oh, it is shift. No, it's shift left, because if you take the topmost. What? Whoa! Why does it? Oh, 15 goes to 0. Okay, that is in fact shift right. Okay. Anyway, I screwed up the design because it's actually supposed to take the signal elsewhere, otherwise it's actually supposed to not redirect the signal if it's off. So we have to take another input. Hold on. Then I'm gonna do this. Read into an AND gate, another write, and then somehow do the read here as well. Fuck me. It's hard. Seen people do a shit ton of designs for this, yet I myself don't remember how to do this. But I do remember doing it at least once. I could have sworn to God I did it. Yeah, over here. Oh no. Oh, this design is terrible. Yeah, no. Plus this is in circular shift, this is regular shift, and yeah, it's not good. Also, I'm pretty sure I could just take... No, never mind. Okay. Ignore that. Although I could probably create a unit that is like universal with a bunch of extras. Possibly. Okay. Nah. Okay. Ignore me absolutely tweaking out. You know, VCB is hard. And I'm not harder, sadly. Why am I rebuilding the exact same thing? I don't know. What I can do certainly is what I did there, but that is a war crime. At the minimum. So maybe extend it, hopefully. Wait, hold on. Can't I just read here and put that into an AND gate and then write to another one, which then collects here, and then that read also needs, this one also needs a signal on its own, which is probably going to be the write trace, I guess, if that's an option. But how do I connect it flatly? Can't do that, can I, huh? What am I constructing here? What is this? I cannot put it there. I can only put it here. And that makes me sad. Slightly. Phew. There's no good way of doing this. Unless I directly put the AND gate onto the bus, which makes it look absolutely terrible, by the way. Don't ever do this, please. It ruins the stacking, but I don't have another option. Okay, let's work with this. Hopefully, it does need some extra, like on this side. Actually, I could stack it directly here. Ooh. Okay, so here's this AND. So there's these two reads, right? Which also will be part of this contraption, and that should be it. So we can just frankly delete this and use our newly constructed thingamabob, which is definitely anything but optimized. And extend it upwards by 4. Yippee! By 4, is it? Because this can shift by 1, 2, 4, 8. Yeah, that should work. So by default, this should just let through anything. Though I haven't really connected the traces properly yet, so except this time they're offsetted by 5, so it's even bigger. But you know, what can I do? Absolutely fucking nothing. So here they output to their corresponding ones, while on the other ones they output to their offset ones. So this one takes 1 as a base, that one takes 2 as a base, that one takes 4, and that one takes 8. Hopefully. And can delete this part, connect this up on the top, and copy this over. And I'm not gonna put anything at the end because I'm lazy, but that means that if I say enter 5, it's not working. So read into that, which what? Oh, wait, what? No, because it reads into that. That's one input. There's another. Oh, fuck! I'm stupid. It's because now it thinks that it's a shared. Oh, it thinks that the whole row is an AND gate. That's not good. That's not what we actually truly want. So we can start again for the 3rd time. I really don't want this thing to get too big. I don't want it to be oversized. Okay, so let's just get rid of this. And since we're here, well, actually, hold on. Doesn't that no? I can't connect it because of the trace. Fuck. Okay, where do we want to fit this in? Probably here. So actually height is actually what we have to sacrifice here. So we're gonna make it free wide and somehow stackable. So we're just gonna take this onto a bus and put this here. So that means we can continue. Very nice. Actually, we could take the AND on the bus as well, which would occupy more space, maybe? I don't know. Let's do that. And so here, now that means that I can freely take this, put it onto an AND gate, and this can work. And we would also somehow need to wire up there too. Hold on. Let's do this, and on this over here. So that ends up reading like that. And then I can actually put this onto a bus now. And there's gonna be, or we could put it onto a tunnel, and we can output it somewhere else, so we can have the whole space for us. That is very nice, except the tunnel cannot take the bus in, so we're gonna stop that from happening. Now in here, we do have read onto the AND, and we can put it here. No, we can't, because it will think it's a whole one. And here, so let's put this here. Let's actually move it one up, just so that we have some, safe space. Read, that's not gonna turn out very well. So read has to be adjacent, and then we have to put the end here, and then we have to read in the other value. Okay, this is hard. So we take this value, right? We read it into the AND gate. Actually, hold on, we could also use tunnels here too. So we could go ahead, get a tunnel here, and so we extracted that. Now let's move this away. Now we can put it there, right? And in between, what we can do is add the output of the write into a bus, which then we're gonna take out here, so it's gonna be parallel. And from the bus we take the write, and you have to somehow input it, but oh no. Okay, that's an issue. Maybe move it one up. No. Oh wait, hold on, I can do this, right? Have the hole here, and there comes out the, oh no. Back to square one, I guess, again. And we haven't gotten any further. Because then if you put it here, get it, then it's gonna take like the entire thing as like one AND gate, and that's not what we want. So so what if we don't get it out there? So this take a read, write, oppa, wrong tool. So like this, maybe a write, and then a tunnel here, this here, and that should work. Right. And then we can put this back on top with an offset, of course, and hopefully this should work. So here's the read trace, here's the write trace, and also the 0 trace. So let's see. By default, right, by default the write is going to be on, but if we enable this one, it's going to shift it over. So far so good. I could definitely do this in a smaller area, likely, if we have two signals. Let me try. So what if I have a 4 base? Because then I could probably do the same, except even better. So this here, so we have a read with the trace, then they do have one shared input, and that makes me twitch. Like, I really want to do that. I really just want that shared input to somehow be truly shared, like with you know, a read on top, and you know, this, like, you know. Let's see. There has to be a smaller way of doing this. There has to be a smaller way of doing this, bro. This is terrible. This is just outright terrible. Like, all this for a mux. All this for a mux is terrible. Like, this is a war crime over here. And this is even this. Oh no, wrong tool. So this is in this is like gonna be gigantic. Oh, and the inputs don't even line up properly. So it's even bad. It's just outright doesn't work. I can't, bro. I can't keep doing this. I really just can't. Okay, scratch this one. Let me look through my projects. This one definitely doesn't have a shifter. 8086 does have one, even though it's an unfinished project. I'm pretty sure I never got to finishing this guy. But it does have this cool shifter, but it's not circular, and it's also terrible. And what the hell is going on? What is this? What is this for? Now that makes me intrigued. Oh, wait, hold on. That's like a stack clear thing. Okay. Sorry, I'm getting off track. Okay, let's look at this one. Don't I have any here? What am I looking at? What am I looking for? Looking for a shifter. Serialu has one whole contraption in it. The Ultra 8-bit CPU, something I never finished, and has no shifts in it. Great. Even a funnier thing, what is this? Oh, that's definitely a project I abandoned. And it is a 32-bit CPU with this and that. It's like a everything burger. And yeah, okay. It's not what I've been looking for. So maybe install RPU has. It's literally just empty. Okay. The funny. What is it? What is even this one? I don't know. Okay. The Ultra 8-bit CPU. I just checked that out. And x86-32. Oh, this is that 32-bit CPU project I graciously abandoned. Damn, that's great. Visualization. But there is no shifting. Okay. This is gonna be fucking boring. I already know this is gonna be boring, but I literally can't do anything else. Okay, I don't have a better idea. I could have sworn there was a barrel shift module, for God's sake. Barrel. Let's search for barrel. That shit. This one. Oh. What is this? More. Huh. Isn't there like a 16-bit shifter? Oh, the barrel shift is one thing. I actually don't know what the algorithm behind it is. Why isn't it? Great, Discord is stuck. Hold on, I have to import this to sight read it even. Oh dear. Jump scare. So what is this? What is the logic behind this? There's 5 layers, yeah, but how does it work? And why does it have 3? Oh, those are the same things. Okay. Huh. Oh, so it just automatically outputs it there, which sure. So I'm guessing the outputs are 5s. So if I do this, it outputs the default. Okay. Then there's the one that shifts by 1, the one that shifts by 2, then 3, then 4. I get it. Barrel shifter is a layer by layer shifter. You have to specify how much you want to shift. But okay. So it's kind of attached to a decoder. That's sadly not what I want. So what is the idea, right? We take a trace, we read it into an AND gate, which takes another input that tells it, you know, how much to shift by. Hey, hold on, now I'm thinking, what if we don't shift the output? What if we shift the input itself? Because that's also an option, and that means that the two AND gates can output to the same input, and then the right signal, no, that wouldn't be shared still, but instead of splitting the output, you split the input. So it would be, so let's see, the one way you can do this is this, right? Like this way you can fuse them together, and then I know that a NOR gate is essentially an AND gate, but like inverted inputs. I know that. So NOR gate is an inverted inputted AND gate, and we could use that technically somehow, because then it would take the polar opposite of the input. That's actually not good, but people have used it, because then on is represented by 0, and that's how the register file works. That's why it uses so much NORs, is because if it's off, that means that means 1 technically, because it's a bit complicated, but take it in, and the input line is inverted, and so the data is technically also inverted as well, and that is 2 inverted inputs, which means technically no, I'm not gonna use NORs. No, that would just make it bigger, I think. So 2 AND gates, right? We share the output, only the input is different, and that's what we manipulate, which input to take from, and that is what's gonna be controlled by signals. So we're gonna have this running through. Okay, scratch that. We're gonna have the read over here, and then we can take this here and read there, and have another read, which then could connect to the bus itself. So it's kinda shared, but it works. It works. So now we just, oh, okay, that's an issue though. Oh, but I need to do this anyway, because I can't just directly connect it. And that should actually be good. So I can just stack it a bunch of times, like this, and that should add up to 16 if I am not failing math class, which I'm not doing to my best knowledge, even though it's summer break. And we can delete these excess chunks that we don't, wait, what? No, I actually do need it because of the input. Only the top layer doesn't need it, but wait, no, the top layer also needs it. Never mind. And I'm seeing a whole lot of nothing. Nice. And so that means that each layer's shift is on the this line, right? And let's see, so if we want to shift over, that has to be on, otherwise it has to be off, and then boom. Yeah, that looks beautiful. I know, it's gorgeous. Okay, very nice. Just gonna copy paste this over a bunch of times, and that should be fine. There's a 2, 3, 4, 5 offset. Hopefully, yeah. And actually, the first layer is really just the toggle layer, isn't it? You're gonna skip that. I'm gonna configure that later. Actually, no, because we can just take the output. What am I talking about? We don't need 5 layers. We only need 4. So now we can do what we want. So we either keep it. No, hold on. There's the other one. We either keep it, right? So we either keep it or we shift it over by the desired amount. So in this case, actually no, hold on. What if we want to shift over by 0? Oh, you can just enable. Okay, scratch that. So if we shift over by 1 to whichever direction, let's say I give it 1 here, that means that whatever you're inputting is going 1 to the left, so it's gonna be shift left, I think. Hopefully, if my intuitions aren't wrong, it is shift left what I'm making right now. Actually, hold on, we do need it because we need our input and output. Oh, someone came home. Give me 1 second, guys. Alright guys, I have to turn up the feed because I have to be quiet because someone is home. My dad, and he doesn't know I have a channel. so we're gonna be streaming very quietly. Alright, let's continue. Either way, what we want to do is test this, right? I wanted to test it. So let me check. If I put this on here, and just as a test, put this up here, see the output work. So, oh, that's because I didn't attach the outputs, Makes sense. They are the exact same, hopefully. So, let's see. Very nice. 5. If I shift by 1, something isn't right. Oh yeah, probably the fact that I need to write and then read. So let's try it again. Shift over by 1 works very nicely. Then shift over by 2, 3, very nice, 4, 8, shift over by all of them. Okay, nice. So that's circular shift working, and that means that if we have, this is circular left shift, then what we can do is copy over the exact same thing, and all we do is that the traces that we put in there, right? See this layer, infinite starting at 0, we start from 15, then 0. Next layer starts at 14, and this starts at 11, I think. Should be. And then this one, which is 7. So hopefully this should also work. So when I say 1 and I shift over by 1, it ends up over there. If I shift over 5, nice. If I shift over all of them, I should have 10. What? That doesn't match up. Why does shifting over by 12 do that? I input there, and then it inputs there, then shifts it over 1, 2, 3, 5. Okay, that means I miscalculated something. So 14. So is it 12? It's supposed to start from 12, because there's 3 in front of it. Then it has to have 5 in front of it. So that is the correct one. This is supposed to be right. And then this one is supposed to be the next one. Did I miscalculate seriously? Huh. That's weird. Loud ass machinery. This should be right. Hold on. Why isn't it working? Let me try to just track 1 bit. So here this shifts over, yeah, it shifts over 2. Hold on, this should make it easier. So this shifts over 1, 2, 3. That's so good. This shifts over 5. Why does this work then? Is that the third one compared to the original? So this should be at the oh, wait, what? Oh, because I'm calculating incorrectly. Hold on. Holy shit, math isn't very easy. Well, that means that this is also 8. Then it should work now. So let's just test it. Shifts over by 1, shifts over by 2, shifts over by 4, shifts over by 8. And all of them should give us 1. shifting over this should give us 10. Works like a charm. Although technically we could use just one circuit and have a setting whether we want positive or negative. Because if you shift left, right, that's already coded. But if you want to shift right, then all you do is just add the inverse, right? So if I have 5 here and I want to left shift by 3, right, that's the same as entering 5 here and then shifting by the opposite, which is this, and it yields the same result, but it's twice as much hardware. So what I could do is delete this, keep this one shift left module. I'm just gonna comment next to it that this is shift left. There we go. It should be CSL actually. The CSL, circular shift left. And I'm wondering, can we modify this so that it works as a regular shift? Because then that means that we cannot loop over, which essentially means that you see these like you see how there's a 0 here and the 0 1 and 1, all those. Technically all we have to do, I think, is just disable that gate. So no, hold on, that would be complicated to do, so I'm just gonna do a separate unit of it. So let's do a regular shift, which is very simple. Although the regular shift does require 2 modules because it depends which way you're doing data loss. So in this one, so that means that, for example, here 15 is only like just an allow gate. Because then it's shifted over very nicely. For example, 0, if you shift left, it just gets lost, right? That's how it's supposed to work. So in all these cases, you just delete these parts and turn them to just allow gates for those. So take this, clump it all together, and that should already do most of the shifts. Already we can do a bunch of this. So if I entered this number at the beginning and I start shifting over, you can see that it just gets lost as is. Very nice. And now all we need to do is do the last layer, which technically is just taking this layer twice. So I can delete everything up to 12. I said I can delete everything up to 12 and just paste this in next to it. And delete these. And also push them together. And that means that shifting is 3 over by the maximum gives us that 1. Very good. Now, that's very nice. Okay. Now we do have to do the same thing for shift right, which also requires to modify some of the inputs. Because then what we have to do 16 5, not 7 5. So that is right. But now this guy and this guy, then fuck this guy. Is that right? And then this guy. No. Hold on, what? Yeah, that guy. I didn't check on. Oh fuck! I didn't check off multicolor traces. So now I just screwed up. There we go. So that should first off start shifting the opposite direction to the right. So 1 works, 2 works, 4 works, 8 works. Very nice. So now what we have to do is that over here where it's like an option to shift these as well, you can just delete them. $14, $15. You can just delete these and then later you can just push them together to mask them. So I need a little bit of movement here and there, but ignoring that. There. Also move these. And then the last layer as well. And then I'm gonna do the cleanup part where I just get rid of the useless bits as well. Because I really don't want to make a circuit that turns into a turns the circular shift into a regular shift, because I don't want things to get too complicated. I'd rather have 3 separate shift circuits for the entire thing. There we go. Put the rest of it right after. There we go. And then we can just delete these trailing buses because we don't use them. And this should hopefully now perform shift left properly. It's like this. Shift 1. Oh, sorry, shift right. Delusional. Shift 2. Shift 4. Shift 8 of them. If I turn it into a checkerboard pattern, it should work. So 1, 2, 4, 8. Like it just works, which is very nice. Because then that means that we can just move these together somehow. I don't know how I plan to do that, but I can just remove these dummy inputs. I don't really need them. So this is CSL, right? This is the shift left module, the regular shift left, and the other one is the shift right module. Very nice. Okay. Now we got both of the modules and also circular shift. So that means you can somehow squeeze them into this ALU, which probably isn't gonna be the most exciting thing, I know, but we can directly get the inputs from here and then the output as well, which is very nice. Though the second input might need some tweaking with it, but so actually I'm just gonna repeat 3, not 2, but actually 4. Hold on. I'm gonna guess an offset of 7. Close, it's 8. Okay, can delete this as well and do the same thing to them. And then I think I can actually color them yellow, not because they're control lines, but because they are a separate data line that don't do regular data stuff, you know, if you get what I'm saying. So, oh, and before I forget, we do need an enable circuit on it if we want to use them, you know, because that is what's gonna be connected to the control line itself. For now, I'm just gonna leave these guys alone. I didn't want to add another one of this guy, which all it does is invert the input, or decrement the input by 1. Sorry, I am saying some bullshit right now. This is gonna be probably trace 8 on the control line. So that's nice. I don't know how much space this is gonna actually require. I'm also gonna add this. And so this is where the magic begins, because I have these secret formulas up my pocket. And right over here, this is a decrementer unit, which is beautiful, and it's oriented in a very weird way. It has the traces in a backwards order, which I don't like, in all honesty. So I'm gonna switch that around and and that means you have to swap traces. So 7 and 0 swap. 1 and 6 also swap. That's 10. This is 6. This is 1. 4 swaps with 3. And 2 and 5 also swap. And that covers all of them. Oh wait, but hold on. This is 1, right? So we put a 1 here. 4 swapped with 3. 2 swapped with 5. And those are the only 3 tunnels, right? Hopefully that's the case. Okay, it doesn't crash out. That certainly means something. So that means, and by the way, wait, hold on. That is not good. This is not the 0 bit. Get it, because it's actually have to be shifted over by 2. So anything becomes 2 less, and with the circular one so that it doesn't get confused. So essentially what that means is that 1 becomes 0, then 7. And is that, yeah. 0 would become 6. 3 becomes 1. 2 becomes the 0, 5 becomes 3, 6 becomes 4, and 7 becomes 5. And that should still work. Oh no. Why is the 2 trace missing? That's probably not good. That means I missed something. Then there's a doublet of something. Yeah, there's a doublet of 4. I forgot to decrement 4 from what I see. Wait, there's no redo button? Why the fuck isn't there? Okay, okay, that was nice. So 5 turns to 3, right? 4 turns into 2. 6 turns into 4. 7 turns into 5. And that should be okay now. Oh no. Right. This one. Haha, there we go. I didn't actually test it yet, so I should probably do that too. And I think we only need these guys. One, okay, 2, 3, 4, the maximum. Good. Works. So now we can get, frankly, rid of this, because now we got the actual decrementer unit. So we're just gonna attach it right here. Take this part out. Bring it down. Yeah, I know this looks beautiful. Absolutely beautiful. And actually, you know what? Let's make it look better. There we go. much more readable. And we need, of course, traces 0 to 6, I think. Yeah. Okay. 6 times with 2 offset and multicolored traces. Nice. Why did my mouse teleport? Did I hallucinate that, or did that actually happen? And yay, that is the decremented one, which literally is the exact same, except it just decrements it by 1, and that is because of the read, which I explained at the beginning of the stream. But if anyone wants an explanation, I can give it again. So okay, so what we have to change for sure is that this guy actually extends further. So this should also be a green bus. So we take it down, and now we also have to add these to a control line, but I think I'll do a separate one. So it's gonna be a pink bus, and that's gonna contain a bunch of special controls. So the pink bus is gonna run through here. And let's see, 0 to 5. They can either be -1 or just any value. So I'm not gonna control. I'm not gonna control them by a actual line, I think. I might add actually an enable on them. So this separated, read, and another read because I forgot that. Right, and 2 crosses. So let's make it 0, and this one will be color 1. aka white. Boom. And we can also move this here for even less elegance. And we can just extend this right onto that bus. There's something in my eye. Jesus. Okay. Let's see. Let's see. Okay, that should be good. And we can connect it up very neatly, may I add. Okay, the input is taken from the exact same one, so while this one calculates with 0, right, this one calculates with -1 right now, which means you shouldn't call read because it will try to read the top of this stack. So I mean, it depends on where the 0 is. If this is the 0, then it's gonna be it will try to read this one, which circular. We get circular. Fucking. Jeez, I can speak. Circular stack. That. Okay. Let's bring it out here. Oh no, that's not good. There we go. We're gonna move this and again add the toggle. Except, fuck. Except this time the colors are gonna be different. So this one will be 2, and that will be color 3. Like that. And I'm guessing the offset can actually be shared. And also I feel like I feel like I should color this yellow, because it's not a traditional value, it's a separate one that is immediate. It's an immediate value. Oh, there's an input to this. Oh, I haven't hooked it up to anything yet, huh? I think I was supposed to hook it up to read 1. Pretty sure that's where it's supposed to belong. Yeah. Although then how do you push immediate? Oh fuck. That's the question, right? How do you push an immediate? Because how do you actually do that? Because because you would put it on the right line, but then again, if you put it on the right line, it cannot access it, huh?
Gyakorolnak is különben, tehát hogy azért örülsz, hogy valakivel beszélsz.
Csak gyakorlok.
Csak gyakorol a kiértést.
Meg néha így narrálok magamnak, de hogy ennyi.
Narrálsz magadnak, értem. Jó van. Mindamellett, bár tudom, hogy már többször nem mit tudom én, Isten értessen kisfiam, mert ma van a születésnapod.
Köszönöm.
Boldog.
So, where was I? So I just did this. Oh yeah, I was wondering. So if I connect it to read 1, that means that read 1 would have immediate values, but that's not good. Read 2 should have immediate values. So that means that the read and write bus are shared. Which, oof, that would be tough. That would be tough to do. But I'm all for it. I'm all for it. I'm all for a challenge. After all, I'm doing this CPU. Okay. This is gonna be weird, but if it works, it works. Don't touch it. Okay. Yeah. And then we can get immediate values pushed onto the stack, as well as register values. So you can do a bunch of stuff. Okay, that's nice. I like that. I like that. I like that. Okay. I don't know where to place the shift ports yet. I could wire up the call stack, but I don't know if I want to do that right now. I'm getting a bit bored, so to anyone who tuned in, thank you. Really, thank you for watching. I appreciate your presence, even if it was mere seconds, and hope to see you guys later. Again, sorry for my weird upload schedule, and see you guys, and thank you for watching.